Right. So couple things before we begin today's review. The first thing is this project we have been posted since Monday, and together with the project content announcement. I think most of you have begun to contact your team member, but just in case that you have not seen him or her in person, today will be the chance. Please do meet up during the break. We have the whole next week for you to prepare on your project submission and the project composition. So make sure that you make good use of that time. The submission deadline is hard. So all the teams, all the sessions across the semester, they will be using exactly the same material and will be following exactly the same guideline and deadline. Right, so make sure that you use the next week well, and if you need any consultation, although we do not have class for the next week, but do free to just let me know, so we can probably arrange a time for you to ask question. Or I mean, if you have any question that you would like to ask during the week, just post it on our I think forum is a bit quiet for the last few weeks. So if you have any discussion you wanted to get going, just post it over there. Usually, again, our response time are quite fast. Right, so this is the first thing. All the teams will have two members, except for the last team, because we have an odd number of students in this class. So the last team will have 3 students. Right, but for all the other teams, you'll have 2. All right, so I think this is the first thing to get the project going. All right, so very briefly, just go over, I think, for the content for this week. This is probably in terms of the project preparation, the different content that we have covered this week probably will be most relevant in the sense that it deals with the case where you cannot find exact solution, either due to the complexity of the problem being too difficult, or you just simply have a very constrained execution time, which are both the case for the project assignment that's given to you. If you, I mean, you can try to attempt it, try to, at least for small scale, try to solve it exactly, but very soon you'll discover that as the graph become larger and larger, coming up with even the good answer will be challenging, right? So again, many different ways about how to deal with that has been discussed in various different kind of setting. For the purpose of this class, we introduced 2 of the most useful and 2 of the most popular approaches that people use when they cannot solve the problem exactly. The problem instance that we use is the Shih-Fen problem. If you recall, the same chart we have used when we motivated the use of complexity in doing the analysis. So now I think it comes a full cycle. So at the very beginning, we pose this as almost like an impossible problem that we cannot really solve. But in practice, people solve much larger problems than this one. And a lot of times, even with additional constraint. Just to show you, again, we have a couple of examples that's been highlighted over here. But if you think about that, right? So, I mean, all of you actually order stuff online. If you just imagine that, I mean, one of the biggest provider of logistics service locally is Linjavan. You just imagine if you're at the planning department for Linjavan, the kind of test that you do on a daily basis is that you will receive all this order from like different e-commerce platform. You will have tens of thousands of packages that you need to deliver every day. You have a fixed amount of vehicles and drivers that's available to you. Let's say you have maybe, again, arbitrary number, let's say 100 vans, and you have to deliver like 10,000 parcels. What you need to do every day is that you have to decide, like, how do you, number one, how do you group all these different parcels into smaller groups? And small group, again, based on the geographical locations. You hope that all these parcels that you try to pack a particular van for, they are close by. And then after you have that, right, let's say every van, you designate about like 100 to 200 parcels or packages per day. Then you have to decide on the routing. And your purpose is to allow them, to ask them to finish the test within the shortest amount of time. So that is our TSP, right? Given a fixed amount of tasks, you know exactly what is the location. And sometimes, again, in the case of last mile logistics, sometimes you have to park the car, you have to like push the cart out, and you have to like deliver it to the door front. that take time. So you have to consider that, I mean, given all the different HDB blocks, different condos, different estates, what's the estimated delivery time from your parking location to the actual storefront, right? You consider all that, then you do your routing. So the practice, in the practical sense, the real challenge solvement problem that you're solving will be much more difficult. But over here, I mean, we solve a simplified version. If we can deal with that, then we can think about like how do you gradually incorporate those kind of additional considerations. I think this is one, this particular analysis over here, if you recall, you may wonder why we look at people sitting around a circular table. Right? If you recall, I mean, you have been asked multiple of these complexity questions, but now you know why, right? So you see that if you try to analyze like that, kind of find out the numbers of possibility of sitting people around the circular table, essentially, this is the same as finding the numbers of possible tools in the Chauvian Saltzman problem, right? If you look at this formula over here, it has a very similar rationale in deriving this particular formulation. You have n different CTs, so if you do the pure permutation, a complete permutation, it'll be n factorial, but because it's a tool, so you don't care which particular CT you are beginning with. So that gives you a division of n over here. So now instead of n factorial, you have n minus 1 factorial. And we divide by 2 because you don't care. You do, I mean, suppose the graph is perfectly symmetric. It means that you go from one location, let's say A to B, the cost is always equal to the cost of going in the reverse direction, B to A. If that is the case, then again, for any tool that you come up with, you can do it clockwise. You can also do it counterclockwise. That's why you divide by 2, right? But in terms of the logic, very similar to sitting people around a circular table, right? So I think this is the first analysis that we do. All right, so again, over here, we have proposed like 2 different greedy principles. I think the important thing to note is that for the 2 different type of heuristic idea that we introduced, number 1 is greedy, number 2 is the local search. They are being designed with very different, I mean, in some sense, it seems to be similar, but they are being designed with very different functionality in mind. For greedy-based approach, the most important functionality is in creating a solution from scratch. Out of nothing, you create a complete solution, one step at a time. This is the key. Now, so if you look at, if you're, let's say you are being asked to design a greedy-based heuristic to solve, let's say, a very complicated problem that's potentially combinatorial. Right? Combinatorial means that your complexity is either exponential or your complexity can be factorial. Right? So for those cases, you see that the reason why they are difficult is that, I mean, the only way you can find good solution is that you have to simultaneously look at all the combinations. And greedy-based approach try to break it down. Right? So we say that we don't want to, and we cannot look at the 4 combinations. So what we do instead is that we make one decision at a time. Okay, so I think this is a very key idea, which means that if you are given a particular decision problem, the first thing, if you want to come up with the greedy-based approach, the first thing you need to do is that look at the approach, right? Look at the problem. Try to think about a particular approach that will allow you to make only one single decision at a time. Right? So in this case, we have NCT. We want to come up with the permutation, the best permutation of these NCTs. So we do not look at the 4 permutation. Instead, we look at one CT at a time. If you are standing at a particular location, what will be your best decision from that particular CT? One CT at a time. Now, of course, the trade-off is that because you didn't look into the future, the kind of quality you get will not be so good. But that's a particular trade-off we'll be happy to take, right? But this is the essence of the greedy-based approach, right? So we demonstrate that, I mean, by following this particular design principle, we can have at least 2 different type of greedy algorithm that we can use to solve the TSP. We have this it's a very simple greedy one, and we have a slightly more complicated greedy two. But both of them actually follow very similar idea. You try to utilize, try to enumerate only one decision at a time, right? I mean, but for that decision, you try your best. Okay, so this is the greedy-based approach. And then we have the local search. Local search follows very different principle, right? So if you look at it, the basic idea I think is best illustrated over here, right? So for each and every solution, we will define a neighborhood. That neighborhood basically means that if you only make local changes to your solution, part of your solution, how many combinations, how many additional solutions were you able to generate? You look at all this possible new solution you can generate by making minor changes. You pick the best one and you modify your solution to that one, right? So that will be the local search. The major difference that make it special when compared to the greedy-based approach is that greedy-based can construct solution from scratch. You start with nothing, but after the greedy solution ends, you will have a complete solution. But local-based approach, local search-based approach require you to give this particular method a starting solution. Then you can incrementally improve it until you cannot improve any further. That is local search, correct? Which basically suggests that although like in the context of this slides, we introduced them as if they are fully independent, but they do not need to be so, right? Actually, in practice, they are very commonly being used together. You can imagine that I can use a greedy-based approach to very quickly construct a solution, but then I can use a local-based approach, local search approach to try to further improve the greedily generated solution, right? So combination potentially can give you even a more powerful algorithm. Require a little bit more time, but the end result will be much better, right? So I can probably very briefly just walk you through the implementation. So it's actually in our code over here. If you look at the week 11 code over here. Right, so again, the package is under here. You go to session 11. We have this W11 code. Not sure how many of you actually tried that, but inside here, I mean, if you extracted a couple of files, two up, of course, is the implementation of the local search algorithm we introduced in slide. I mean, if you're interested, you can take a look. You can see that this is the cost before you do the swap. And this is the cost that after you have swapped. I mean, this particular step over here is the two up, right? So you swap two ages, two endpoint essentially, which effectively means that you create a pair of new ages. You calculate the cost, you compare the original cost versus the new cost. If the new combination actually give you better results, then you will keep the new one, right? You keep finding the best possible move that you can make in that iteration. At the end, you will make that move. But in the end, if no further improvement is possible, then you terminate, right? So this is the two up, and we actually have a greedy. If you go into the Graph Lab 2, this is the version 2 of the Graph Lab. You can take a look. If you scroll down, you will see we have a greedy one. Greedy one is over here. This is the implementation of greedy one, and this is the implementation of greedy 2, right? So now we have all the algorithm, right? So we mentioned that combination of these two potentially can give you a better results. So we have this the first example file. This particular file over here pretty much just give you the class example. This is a 5CT TSP example as given in class. We use exactly the same vertex label. We use exactly the weight matrix, and then we use that to create a graph, and then we execute greedy one, we execute the greedy two. Sorry, not greedy two, but we execute the local search, right? That's based on the greedy one. If you want greedy two, actually, we can also do greedy two. We'll just need to copy this and say that this is the greedy two. Let's say this is 1, 2, right? Greedy two. Greedy two doesn't require the initial vertex because essentially greedy two find the best solution for you. Right, the best starting point for you, which is the pair that's with the smallest cost, right? So we can modify this a bit, then we can see the outcome for both the greedy one, greedy two, and the local search. That's based on the solution that we get from the greedy one solution, right? So let's see how it goes. We can go to, this is, I think this is where we are. We can execute this file, the first example, right? So if you run it, you can see that this is the solution that we managed to find. Again, we can go back to the slides, just try to check up on that, right? So this is the weight matrix, which is being used in the construction of the graph. And then we look at the greedy one, greedy two, and then this is the table that summarizes all the possible root cause. The reason why you can do that is because the problem is really small, only 5 cities. So if you use the formulas 5 minus 1 factorial, 4 factorial divided by 2, that will be 12, only 12 possibilities. So we can do a pure elimination and tell you that, like, what is the cost for each and every permutation. You can see that the greedy solution identified 985, but the optimal is actually 940, right? So greedy is close enough, but still not the best. So you can see that this is the execution results. We actually tried the greedy one, we tried the greedy two. The sequence look different, but their cost is exactly the same. Right, so this one you can see that is actually a permutation and in the opposite direction. And this one you can see that is running in probably clockwise, but the greedy two start from C actually and runs in the opposite direction, but the cost is exactly the same. If you check the sequence, they are the same sequence. Okay, so that's why the cost is the same. But you can see that this is actually how we can implement the idea we just mentioned. We use the greedy one to generate a solution close enough, but not good enough. Doesn't really give you the exact. But now if you take the greedy one, you try to do 2 up. You can actually, for this very small graph, you can manage to actually get the optimum, which is 940, right? So this is basically demonstrate that combining 2 heuristics can give you better result. And the combination is actually quite simple. If you look at the kind of combination that you do, let me hide this, right? So we can go to the combination over here, right? So you can see that by running the greedy one, we get a return. This return T1 contains both the value, the length of your path, and the path itself, right? 2 component tuples. And then you can see that for 2 up, all we need to do is that we use the path that we obtained from greedy one, and then we try to run a 2 up. Then we get a new result T2, and that result turned out to be the exact solution, right? So this is a very small scale example, only 5 CT, we can manually do it. But the same idea, I mean, if you wish, you can try it on a larger scale, right? So this is the second example. You can see that for this second example, you can set the numbers of CT to be much larger number. In this case, we set it to be 100. We can just let it run for a while. You will take a while, so just let it run in the background. Then you can see that we randomly generate the graph, which means that the coordinates are all different. And then we have a couple different ways of solving this problem. The first variant, we use greedy one, right? But again, greedy one, you have to specify which particular starting vertex you want to use. So depending on the starting vertex, your value may be very different, right? So what we do to overcome this is that instead of just specifying any arbitrary starting point, we try them all, right? Because executing a single version of the greedy one is actually not too long, quite fast, right? So we can actually execute this multiple times. So what we do is that for each and every vertex in the set of vertices, we execute one version of the greedy one, and we always keep the best solution, right? In the end, what we print out is actually the best solution that we have discovered. So this is greedy one. And then we utilize the idea. We say that, okay, so definitely greedy one is good, but it's not going to be the best, right? So we can use the local search upon the best solution we have discovered by running the greedy one, right? So we execute the 2 up based on the return value, right? And then we print out the value again. So this is the first way of combining the greedy one and the 2 up, the local search. All right, the second approach follow very similar idea, but we say that, okay, so instead of only applying the local search after your greedy one actually have identified the best solution, we can actually execute a local search every time. For each and every greedy one solution we obtain, we'll try to improve it until we cannot improve any further, right? So that result will be stored in TT. And then we actually will be comparing TT against the best solution that we have accumulated so far. So you can see the major difference is that for the first one, the local search is outside the loop, right? So we only do one local search on the best greedy one solution. But the second version, for each and every greedy one solution, we try to improve it. And we try to preserve the best solution out of those improvements, right? So this is the number 2 approach. The number 3 approach, we have this greedy 2. Greedy 2 really, you cannot do much, right? Because unlike greedy 1, you have no ability to control the execution of the greedy 2. Greedy 2 will automatically select the age, the pair that's with the smallest cost. And you try to expand your tool from there, right? So what you can, the only thing you can do is that you can first execute greedy 2, print out the solution. Then we print out the result, which is after you get greedy 2, you try to use local search. Right, final result over here, this is just for comparison. We say that, how do we know that the heuristic is actually good, right? So one way, which is the random search, we kind of mentioned that this is one possible strategy that you can use when you try to solve the challenge salesman. Given a fixed amount of time, let's say you have 2 minutes, right? You just generate as many randomized solutions as possible. But here, this is a variant, right? So we say that we don't just generate random solution. For each generated random solution, we try to improve it, which is over here, also using the tool up. We try to improve this solution as much as we can, right? And then we will use the that improved solution to find what is the best possible result we can get. Over here, we only do 10 repetitions because really this is very time consuming, because randomized solution generates something that's potentially very bad. So when you feed this randomly generated solution to the local search, which is tool up, potentially it can take much longer time than you feed already quite good solution, which is the greedily generated solution, right? So you cannot afford to run this for too long, right? Okay, so this is the result. Let me probably make it slightly larger so you can see. Right, so you can see that there are a couple different versions over here. So you see that this is the graph, randomly generated graph with 100 different nodes. If you use only the greedy one, but you enumerate all the possible starting nodes, there are 100 of them, right? For each and every starting node, you execute one copy of the greedy one, and this is the best result that you can get. The time it takes about like 2.5 seconds. So roughly speaking, for every instance, every greedy one, it takes you about like 0.02.5 seconds, 0.025 seconds, right? So which is quite fast. The second approach is that for the obtained solution, you try to apply tool up to it, right? So you can see that there's always room for improvement. So tool up indeed help you to improve the best greedy one. The third variant over here, you can see that for every possible greedy one solution, we try to improve it. And then it turns out that the time it takes, I mean, although the time it takes is slightly longer, but the solution quality is the same, right? So again, this is randomly generated graph, which means that if you just randomly generate another graph, the result might be different, right? But you can see that if you want to execute local search still takes time. So if you do it on each and every potential starting point, you generate the greedy and then you use the local search, right? So it would take slightly longer. That is the trade-off that you have to pay. And then we have the greedy 2, right? So you can see that when you compare greedy 2 against the case of greedy 1, where you pick the best starting node, greedy 2 turned out to be giving you like worse outcome, right? But if you look at the implementation, actually greedy 2 is much more complicated than greedy 1. Later, we will analyze their complexity as well, right? So what we can get out of this is complexity, the heuristic development doesn't favor complex solution, necessarily. Sometimes you can create something that's very complicated. It actually benefit you, but there's no rules to say that, oh, just because your heuristic is more complicated, more sophisticated, you are going to get better solution. In the case of greedy 2 and greedy 1 comparison, you see that empirically, there's no relationship. Although you can make it much more complicated, but the idea in practice may not work too well, right? So this is the pure greedy 2. You can try to improve it. The value does improve if you look at the ratio. The improvement ratio is roughly speaking 5% after you apply 2 up to it. But still, I mean, it's not as good, about like 10% worse than the case where you apply greedy 1 and also the local search. Okay, so this is greedy 2. And the final approach, this is just as a comparison baseline, right? So we try to fine-tune the numbers of repetition. You see that for the greedy 1, for each and every starting point, you try to apply local search. You pick the best one. This particular option take about like 10 seconds. So we fine-tune the numbers of repetition. So this randomized solution generation plus the local search take you about roughly also 10 seconds, right? You say that if I give you the same amount of time, which is 10 seconds, how good will you be able to generate your solution? It turns out that it's actually far away from the best possible solution you can generate with the combination of greedy 1 and 2R, right? So the differences is almost 50%, right? The solution is actually 50% worse. All right, so this is empirically how we usually evaluate different implementations. So unlike the exact approach, I mean, exact approach, you're always being guaranteed that you're going to have the best solution. So all you need to care about as a result is how long does it take for me to achieve that objective. But for the case of heuristic, you do not have that guarantee anymore. That's why usually, if you really want to, I mean, if you have some idea, you very quickly cook up an implementation, test on a very small scale problem seems to be working well. In terms of the more realistic evaluation, this is what we will need to do. Here, we only do it for a single randomized instance. If we want to generate something that's more convincing, what we need to do is that we probably have to repeat this process for sufficient numbers of times, let's say 50 times, 100 times. So you have accumulated performance statistics for a lot of different random instances. Then we can empirically write down for every different combination or different implementation of your heuristic, what is the solution quality you can achieve and how long does it take, right? So you can try to, for example, instead of 100 nodes, you can try 200, 300, 400. You see how well your algorithm scale and what's the best algorithm combination when the problem size really become large, right? This is what we care about, right? So usually this is where a pipeline, hopefully automated pipeline, will be really useful. I mean, you try to pipe a real problem instance to it, and you try to check on the real performance by using the realistic data that you have produced. Okay, so I think this is actually the same that I think hopefully after we conclude this particular session, you'll be able to do. Very similar thing you can see that when you try to solve your project problem, you'll face very similar kind of requirement, right? So I mean, the problem cannot be solved exactly. So you can probably think about a couple of different heuristics. And here we already have like at least 2 different heuristic idea for you. If you count in, for example, genetic algorithm, that's another potential idea, right? So you can try to think about like what is the best way you can combine all these different methods to address the question that you may have. All right, so this is the implementation part. And again, heuristic is very computational, right? So if possible, do just set aside some time, just at least download the code, run the code, modify if you want, modify the code a little bit, try to conduct your own experiment, right? To see like what kind of additional improvement potentially you can make. Okay, so before we proceed, I think before the class, I saw that there are some questions being posted. The 2-up analysis, y is actually n times n minus 3 divided by 2. Okay. Right, so let's go to the corresponding slides over here. Yeah, this one. The performance analysis, I think is somewhere, yeah, over here. Okay, so again, it's been explained in slide, but just in case you don't really catch it, just remember one thing. The local search operate unlike the greedy-based approach. If you look at the greedy-based approach, the decision you are making is always on the node, right? Node represents city. When you are at a particular node, the greedy-based decision is which particular next node do you want to pick. But for the local search, that is not your consideration, right? For local search-based approach, you are given a route already, right? So for example, this is like one potential case, like 5CT case. You can generate something that not so good, right? Something like this, let's say a star shape. This is your current route. So what the method will do is that if you look at this, you have a case where your n equals 5. If you count the numbers of edges actually equals numbers of cities. It's also 5. It equals n, right? Because this is the tool. Okay, so what you will do is that in terms of analysis, the local search-based method is age-based, is not node-based, right? This is the first important distinction, is age-based, which means that when you make the selection, you are selecting, as I use a different color, you are selecting ages, right? This red ages is being selected. So now what you intend to do is that you want to select another age that doesn't overlap with your endpoints. For example, you select this one, and what you do is that you're going to delete them from consideration, right? You delete these two from consideration. Okay. All right, so now these two ages goes away, right? What you want to do over here is that you will want to reconnect them. Right? Previously, is this and this, right? So you want to find out what are the alternative ways where you can reconnect this, right? So you have one endpoint, endpoint here, and this is another pair of endpoints, right? So if you do not, you want to use this like cross shape, what you can do instead is that I say that I do not want to connect this to this, right? I can instead connect this line over here to this line, and this line over here to this line. Right, so that will give you like another route, right? So you can see that because you do not have crossover, this route will actually give you a better cost, right? So this is like one selection. Okay, so of all these different potential ages that you select, in total you have n possibility, right? So you can choose any age. And then once you pick the first age, right? So let's say, for example, in the previous case, I picked this age. What you would like to ensure is that the other age that you are selecting, let's say over here, right? So originally, I make this selection over here. The age that I cannot select are the age that's already connected to my endpoint, which means that this one, you cannot select. And if you look at this one also cannot be selected, right? So that is actually the limitation, right? If original, just go back to the original selection. Okay, let me redraw it, right? So this is the, I'll say 5CT case. Right, let's try to probably draw it like in the polygon, make it easier to see. Right, so let's say your first age that you select is actually over here, right? Our requirement basically say that this age you cannot select, this age you cannot select, because if you select these two ages, you only have 3 endpoints. And 3 endpoint, the only way you can reconnect is to recover the same age, right? So if you want to have the ability to create a different way of connecting your paths, you need to select all the other ages. In this case, it's 2 ages are okay, right? All the other ages that does not directly connect to any one of the endpoint, right? Which can be, for example, this one, right? So you produce this particular endpoint. Then you can say that instead of the current 2 ages, I can reconnect them, reconnect the endpoint. Then I can generate a new path, right? So that's why you cannot, for each and every age that you select, you have originally n-1 candidate that's out there, potentially you can choose. But the 2 ages that's connected to each and every one of your endpoint, you cannot choose them. So you you subtract them away from the choice. That will be the total numbers of selections. And of course, you have to divide by 2 because when you, for example, if you are at this particular point, you can choose this one, but when you are at this point, you can also be choosing this one, right? So I mean, you want to divide away the duplication, right? So that's why you divide by 2. Okay, so this is the complexity for the local search, right? So any question before we go on to review the show quiz? This page over here. Okay, so let's look at the show quiz. I think not all of you have finished that, but again, this is something you probably have to make up after the class if you have not finished this set of questions yet. For this week, actually, we have a lot of questions. I think this is the week that we have the most numbers of questions. We have in total 11, right? I mean, some of that early on, I mean, they are mostly fact-based questions. The first one, I think this is the variation. Just basically test you whether or not you understand why we divide by 2. The reason why you are dividing by 2 is because you recognize that it doesn't matter which direction you are going. You can go clockwise for a tool. You can be doing the opposite direction. But the assumption that will make it work is that it doesn't matter which direction you're going. The cost is always the same. So what this particular question over here asks you is that if the graph is not symmetric, it means that the cost going from A to B may be different from B to A. That's the case that we talked about earlier. Then you cannot divide by 2. But you can still rotate, right? Because it's a tool, so you can pick any city along the tool to begin your tour, but the total tour cost will still be always the same. Right, so this is the first one. This is the reason why is n-1 factorial. Question 2, yeah, this is like just 2 different approaches that we have introduced. If you look at genetic algorithm in a way, that's you can probably also view it as a form of local search, actually, because again, the way solution is being generated is all based on your current solution that's in the population. For each and every solution, you try to find different ways where you can vary it, right? And then you just make it rejoin the population. And for the solution that's not so good, you don't dump it straight away. You use probability to choose which particular solution you want to eliminate, right? So that's a special kind. I mean, you can view it as a special kind of the local search algorithm. Right, so that's number 2. Number 3, I mean, from 3, 4, 5, 6, they all use the same distance matrix. For number 3, this is what? Yeah, simply just applying the formula. You want to like look at this is 5 CTKs. How many potential paths you can generate? This is a classic example. Actually, you have a case of 5 cities. So 5 minus 1 give you 4 factorial, 24 divided by 2, you got 12, right? So that's the numbers of tools. Okay, so this is the direct application of the formula that we see, question 3. Question 4 over here, we begin to practice, I think the first, 2 greedy 1 practice and 1 greedy 2, right? So let's very briefly just walk over that. Let's use the first. Look at the first greedy 1. Right, so this is our cost. Again, for greedy 1, you have to specify your starting node. The first example, question 4, you start from CTW. Right, so this is your starting point. Again, you can make a note to make sure that you don't accidentally just select a city for the second time. So you are at W. So just to remember, this is greedy, which means that your choices is associated with only your current location, right? So now you are at W, right? That is your current location. So you look at all the outgoing links, which one give you the smallest cost? It turned out to be Y, right? So you pick that. That's the where the greedy part actually come in. So the cost is 2. So now Y is being chosen. Again, you cross it out to make sure that is clearly noted. Now you move your location to Y. This is your point of consideration. So you look at the remaining choices. You can choose 3, 5, and 2. 2 turned out to be the best choice. That would be A, right? Give you a cost of 2. And then, so you remove that. So now you move to A. You look at A, the remaining choices, 4 and 1. 1 is with lower cost. You choose that. That will be Z, right? So you move to Z. The cost will be 1. Again, remove that. So now you are at Z, right? Only one more choice remain, which is 6, right? So you'll be 6. Go to X, right? But again, this is the part that's easy to make mistake. Remember, this is not a tour yet. You finish the path. You reach your destination, but you still need to reach the beginning point, right? Your beginning point will be the CTW, right? So you have to go back to W, right? And so which means that if you want to calculate the cost, you have to look at from X going back to W, your cost is actually 4. This will be your cost, right? So if you calculate the total cost, you sum up all the numbers along the way, it will give you 15, right? This is the total cost, right? But this is the sequence of the visit. Okay, so this is the greedy one approach. You can look at the solution. This is the past, the visit sequence that we come up with, right? But again, with the hidden assumption over here is that you must note that the moment you reach the final city, you still need to go back to the very first city. If the question actually asks you to quantify the cost, then I mean that is what you need to report, right? This numbers, the last city over here, very easy to mix, right? Make sure that you always include that. So this is the first greedy instance. You start from W, right? The second instance, you can do still greedy one, but you start from X, right? So let's look at this particular instance. Still follow the pretty much the same tracking procedure. Start from X, okay? So this is our very first city. Again, remove X from consideration. We have X over here. From X, again, you pick the one that was the lowest cost. Just in case you have tie, it's up to you to discuss how you will break the tie. You can break the tie randomly, or you can break the tie following, I don't know, maybe alphabetical order. But usually randomly will be a better idea, because then it means that if you run the algorithm multiple times, potentially you will have the ability to discover a better solution, right? So your first decision will be Y, right? So again, you move to Y, so you cross out Y from consideration. So now you can see that you indeed will encounter this, the case where you need to break the tie. You can choose W, you can choose A, right? Let's say we pick the first one, right? So we can choose W, right? Later we can try choosing a different one to see how it goes, right? So now we move to W. From W, you can cross out W. You can choose the remaining city. I mean, A will be the next city that you choose. Remove A, you move to A. Then the final city will be Z, having a cost of 1, but you need to return back to X. So from Z, return back to X, you get a cost of 6, right? So if you calculate the total cost, the cost will be 17, right? Which is higher than the case where if you start from another city, the previous instance, if you look at the previous instance, starting from W actually give you a cost of 15. Right, so this is one potential way you can break the tie. So we can restart this. We can say that, okay, so now, I mean, when it comes to breaking the tie, we choose the second possibility to see whether or not it generates any differences at all. So you still are at X. Your first choice is still Y. I mean, this part doesn't really change. But Y, from Y, you can actually choose W and A. We already have a case of W, so we choose A in this case. So we choose to A, And then the cost is 2. From A, we make the choice to Z with the cost of 1. From Z, we actually move to, only one last choice. You can only pick W. The cost is 7. And from W, you can return back to X, which give you a cost of 4. Right? So if you quantify the cost over here, the cost here turned out to be exactly the same, also 17. Right? So it turns out that it doesn't matter how you break the type back then, you're still going to get the same cost. But again, I mean, there's no guarantee, right? So potentially, I mean, there's 2 paths can give you different costs. Okay, but the real answer that you have to report over here is XYWAZ, or potentially, if you break the type differently, it's going to be XYAZW, right? So that will be the 2 cases that's being reported over here. Right, so that is the greedy one. Greedy 2 this is slightly more tedious, very easy to make mistakes. So make sure that you document everything very carefully. Yeah, so over here, I mean, we assume that also greedy 2 will select the pair automatically for us, but we assume that just for the ease of comparing solution, assume that we will report our answer starting from A. Okay, but again, we know how it works, right? So if you have a greedy 2, essentially you are looking at the whole matrix, and you will pick the element that has the lowest value, right? So it turns out that this value is the lowest. So if we track the tool, right? This is the current tool CT that's already covered. Is going to be A and Z, right? A and Z are now out of consideration, right? So you have A and Z inside your tool set. So we have A and Z. So now starting from this point on, right, we can go back and we can try to follow the algorithm exactly, right? So this is the greedy 2, right? So what we will be doing repeatedly in greedy 2 is that against the current set of tool cities, you pick another candidate, which is the another CTX that have the smallest distance to all the cities, right? That's already inside the tool object. So we will do that for all the candidates. So now A and Z are already selected. So in terms of the candidate, you still have W, you still have X, and you still have Y, right? So you look at W is actually over here. So you look at the intersection, right? So W intersect Z and A. So you see that the smallest value occurred at 5 over here, which is with the CTA, right? So for W, this is X, right? You write down your Y over here. Your candidate connection is actually with CTA, and the cost will be 5, right? And for X, you look at X, right, which is column X. The intersection is 6 and 4, right? So your Y connection candidate is still A, but the resulting cost will be over here, which is 4, right? The final candidate is actually Y. Again, you look at the intersection Z and A, the candidate connection point is still A, right? But the cost will be 2 this time, right? So if you look at it, Y turned out to be having the smallest potential connection point. So you're going to insert Y into your tool set, but you have to decide, right? So one of the step over here after you make the choice of X and Y, you have to decide, should I insert the new candidate X in front of Y or before Y, right? You have 2 possibilities, right? So in the case where you only have 2 CTs, actually it doesn't matter you do the insertion in front of A or after A, right? So you can do generate exactly the same tool, right? Because think about that, right? So what you have is that you have A over here, Z over here, right? So if you decide that, okay, so before you go to Z, you want to go to Y, right? Then this is the tool that you're going to produce. Versus if you want to insert Y in front of A, what we are going to produce, right now here's A, this is Z, right? Right now, if your Y is actually over here, I say Y over here, means that Y goes to A goes to Z, and then Z go back to Y. You look at the sequence, it's actually YA, if you start from A, it's actually AZY. Over here, this is AYZ, right? So they are exactly the same, right? Because it's a triangle. I mean, there's no alternative way to connect them into a tool, right? So it's just that, do you do it clockwise or do you do it counterclockwise? That's the only difference. So in the case where you are inserting the first CT, doesn't matter where you inserted that CT in front of the connection point, right? The end result will be exactly the same. Here, because the solution require you, if you go back, require you to begin with A, right? So I think the easier way is to expand the tool set by attaching the candidate CT, which is Y, after the connection CT, which is A. So the second tool will be AYZ, right? So now you repeat, right? So now you have a AYZ, right? You repeat exactly the same procedure. You still have W as a candidate, still have X as a candidate. So you look at W, your intersection is actually 2, 7, and 5. 2 turned out to be having smallest value, and the candidate connection point will be Y, right? With the cost of 2. And for X, again, you look at the intersection, the smallest value also occurred at Y, but the cost is actually 3, right? So W will be selected. But now you actually need to consider the 2 different scenarios. What if you insert W in front of Y versus you insert W after Y? You're going to generate two different costs, right? We're going to evaluate them all. The first instance is that you have A, let's say you insert W in front of Y, right? So this is the tool that you're going to produce. For the second instance, you're going to have still A, but you insert W to be after Y, right? So Z is still the same, A is still the same. So if you compare these 2 cases, right? A, Z, ZA, ZA, these are the same, right? You don't need to include in the comparison. And then Y, YW and WY, they are also the same, right? You don't have to include them in comparison. So it turns out that the only comparison that you need to look at is AW, YZ, and AY, and WZ, right? You compare those 2 pairs. Which one has a lower cost? You'll pick that one. All right, so we do the comparison over here. AW's value is 5 plus YZ, right? You look at YZ is also 5. So for this particular order, inserting W in front of Y, you get a cost of 10. For the second case, you have AY over here is 2. And then plus WZ give you a cost of 7. Right? So it turns out that the second order give you less cost. So you're going to pick that. Okay, so if you update, what you will get at this particular step is AYWZ, right? This particular sequence, right? Because this is the one that's with the lower cost. Right, so final step, you only have a single candidate, right? So it has to be inserted. But what you do not know is where is the connection point. So for that purpose, you still need to look at the intersection point. So if you look at X, column X, intersection point is 4, 3, 6, and 4, right? So CTY is still the candidate connection point with the cost of 3. Right? Which is the same as the previous case, right? So now you are going to insert X around Y. 2 different ways you can do the insertion, right? Number 1 case, this is number 1, number 2. Number 1, you do it in front of Y. So you have A, you have X, Y, W, Z, right? And then of course you go back to A to make it a tool. For the second case, you insert X after Y. You have A, Y, and then you have X. and then WZA. Okay, so again, you only look at the ages that are different. XY and YX, they are the same. WZ are the same. ZA, they are same, right? So only part that's different is AX, YW, and AY, XW. All right, so we just do the comparison. AX, over here. AX, you have 4. YW, I think it's over here, right? YW, let's see, is 2. So here you got 6. For the second one, you have AY, AY is actually 2 as well. And then you have X and W. X and W give you 4. Right? It turned out that you have a tie. Right? Again, over here, it indicates that it doesn't matter how you make the connection, it will always be the same, right? So you can write it, you can report your tool to be AYXWZ, which is the second case, or AXYWZ. Right? And you can quantify, you can actually calculate their cost. For this one, you can calculate the cost to be like AX 4, XY, you got 3, YW got 2, WZ got 7, and then Z back to A. Z back to A, you got 1. So if you look at it, the summation is actually 17. Right? If you check the second one, it should be 17 as well. Right? It's because you tie break them. Right. So, but this is the result that you report, either this one or this one, right? AXYWZ. AXYWZ, or you just invert this, AYXWZ. This is suppose initially you insert the first choice, which is the Y at a different place, then you will get a different reporting, right? But they are the same. Okay, so this is greedy 2. Much more complicated actually. I mean, you look at both, if you trace it like by yourself manually, or if you look at the code, both turn out to be more complicated. But again, in terms of heuristic, very important, complication or a complex design doesn't guarantee a better performance. Sometimes you can actually have the best of the both worlds. Algorithm is really simple, but it gives you superior performance. This is actually possible. Okay, so this is the second greedy, number 6. Number 7, local search. This is the fact-based questions. You always need to start with the complete working solution. This is what makes the local search algorithm special. Number 8, again, this is just selecting, just choosing what apply to the two-up operations, a two-up algorithm. Number 9 over here. This is the size of the neighbor. I think one of you just before the class asked it on the forum. Why this is 35 is because we have this formula n times n minus 3 divided by 2, right? So suppose n is 10, you have 10 times 7 divided by 2, you got 35 as a result. This is the size of your neighborhood. How many possible ways where you can alter, modify your solution? And it also basically means that this is how many different solutions you need to look at before you can move on to the next iteration. Okay, so this is number 9. Number 10, this is just to illustrate one very important operation in the genetic algorithm, which is to choose any arbitrary pair, and then you do a swap. This is what we call the point mutation. You only do the swap at a particular point, one point at a time, right? Of course, you can, if you wish, you want to create more variability in your heuristic design, you can apply multiple point mutation. That's also possible. It's just that then you will create less dependency between your current population and the future population. 11 over here, GA. Yeah, so this is basically to discard in half. Yeah, so this is basically looking at the crossover operation. If you look at the crossover operation in the local search, over here, you can see that this is one of the very important design choice. During the natural selection, this is the time when we almost like we remove the solution that we feel that is less promising, and then we replenish the population with a regenerated solution. Right, so over here, you can see that nothing is different. Right, just because the solution's value is low doesn't mean that we would like to eliminate that. Because the reason for this kind of design, everything is probabilistic. It's just that a solution being bad simply means that you have a higher chance of being eliminated, but doesn't mean that you're going to delete that for sure. It's because if you look at the crossover operation, which is over here, right? You can see that two bad solutions can potentially contain certain part of the shape that actually look quite good and we can reuse. And this is the whole point of crossover, right? So if you can manage to like through the crossover process, you can take the good part of one solution with the good part of another solution. You can actually generate something that's really good, right? So this is how GA sometimes has the potential to make the performance lab. That's from iteration to iteration. For example, local search, you don't really see that because the improvement is always based on the previous solution. So the improvement that you're making usually is incremental. But for GA, potentially you can see a jump, a sudden jump in the performance because you can cut like two very bad solution and produce one very good solution. In this case, you can see that you take two bad solution, you cut you regenerate a new solution, and you solve the problem in one go, right? So I mean, GA actually have this flexibility, which is the reason why I mean, doing our demo, you can see that once you turn on this mix, right, which basically means that you allow both the mutation, natural selection, and also crossover, then the performance really improved by quite a bit. Before that, actually, it doesn't do very well. But once you have the crossover turned on, that's basically the most important driver behind the performance gain. Right, so this is what we would like to get. Question 11. All right, any question before we move on? Okay, so again, for this particular part, right, so I think, like, of course, we talk a lot about principles, about algorithm, about complexity analysis. But for this week, I think the most important test that you definitely should do is that you should spend some time run the code. Right? You need to personally experience what is the greedy principle, like try to go over the code. What is the local search approach, right? The heuristic design is meaningless. I mean, you can have a whole bunch of theory about that, but if you cannot actually generate a heuristic on your own, implement that, compare that, this section is essentially meaningless. Right? I mean, everything that we talk about over here only makes sense when you solve real problem. Okay, so definitely spend some time. We have very briefly walk over the code, but definitely spend some time going over the code by yourself, right? And try to invent new ideas. If you have new ideas, you can give it a try. Just based on maybe the code that's given to you as a foundation, try to generate new heuristic. That would be a good way to really expand your horizon. Right, if you don't have further questions, I guess we can like do like more practice for this week. And we do this, and then after that, we're going to break. Right, any more? Not, we can begin. Okay. Okay, good. And JL. Okay, good. Fine. Okay, too bad. I think the last question get you. Okay, let's briefly just go over the solution before we head to the break. The first one, I mean, this is something that we have gone through. Greedy one. So I see some of you try to do it by mental math, which I think is quite impressive. Not sure how you can actually do this by mental math. It's quite a bit of a combination. All right, so just repeat this very quick. Again, you need the starting point. So we look at the starting point that's given to you, which is the D, right? Okay, yeah. Yeah, you start with D. This is your starting point. Remove this. And you look at the smallest value. So F have the smallest value. Right, this is 1. And you move to F. And then B have the smallest value. That give you 4. You move to B. And then E has the smallest value, which give you 7. And then you are at E. 11 turned out to be the best. You move to C. That's the last choice, which give you a cost of 14. All right, so this is where I think majority of you make mistake. I think roughly speaking, half of you make this mistake. Remember, this is the tool, right? So you have to go back to look at the problem statement very carefully. The value you will be reporting, you're reporting a sequence, but the value that you are calculating is for the round trip, right? Which means that although you reach the end at A, you still need to return back to D, right? That complete your tool, and that is the real cost for the round trip. So from A, you still need to move back to D. This is where this difference of 2 actually come from. So if you add it up, this is 5, 7, 12, 23, 37, and then 39, right? That will be your final cost. But this is the sequence of the tool. DFBECA, DFBECA, but the cost of 39, right? So I think this is majority of the error, which I think about half of you actually choose the previous solution. So that is greedy 1. Greedy 2, I mean, we don't want to do the case that's too large. That will be very difficult to do. So we use the 4 CT case. But again, just watch for the distance of the round trip, which means that once you reach the end, you have to return back to the beginning city. All right, so this is what we have. Again, we do not need to have the initial city. What you need is to pick the smallest pair on the map, which is A and D, AD, right? And then you have A and D, just select that. And then you look at the remaining 2. You can have option B. Option B's connection point will be D with the cost of 3. For option sorry, not D, should be C. For option C, you're looking at 2 and 4. So your connection point will be A, your value will be 2, right? So C will be what you choose. For the case of going from 2 CT to 3 CT, don't have to worry about in front or after. The cost will be exactly the same. You get a triangle, so you have a ACD, right? So the final CT, you have ACD. Final CT is B, but you have to choose your connection point. Your connection point is still the same. It's going to be CTD with the cost of 3. But then you have to consider ACD, sorry, insert B in front, right? A, C, B, D, A, right? Versus you have A, C, D, B, A, right? Two different cases. Okay, so again, this one, you don't really care. So in the end, what you really care is CBDA and CDBA, right? These two value. So CB actually give you 7, DA give you 1. This is the cost of 8. And then here you have CD, which is 4, plus BA, which is 5. This give you 9, right? So this one give you a smaller cost. So your tool will be AC, BD, and return back to A, right? So now you can calculate the actual cost. AC is actually 2, CB is 7, BD is 3, and then DA is actually 1. So your cost will be 13. Again, I think there are some, no other ways. No. Yeah, because they're returning back to A. Okay, so that is the question number 2. Question number 3, this is the application of the greedy base approach. So you look at this over here. Again, for greedy base approach, the most important question you ask yourself is that what is your objective that you try to be greedy about, right? Because for each and every step, you have to pick the best option only based on the information about the immediate next choice. But you have to have a very definite goal regarding how do you know which particular option is the best. In this case, your objective is to maximize the sum of the value of each and every node. So that basically means that when you are branching out, right, your objective is to maximize the immediate contribution to the sum of value you collected as you move from the root node to the leaf node, right? So that gives you an idea about how you can do the design. So your starting value will be 2, and then this is your first choice. From 2, you can move to either the branch of 4 or branch of 8, right? But based on the greedy principle, you want the maximum immediate contribution, which is 8, right? And then again, from 8, you can go to 9 or 11, right? Easy choice for you, just go for 11. So your sum, as a result, if you follow the greedy principle, will be 21 over here. Okay, so this is number 3. Number 4, this is definitely not the greedy algorithm. They are fundamentally different. One is the construction-based approach. The other is the improvement-based approach. Number 5, this is the case that we talked about at the beginning of the class, right? So TSP, this is like for a single worker, right? So but here you can imagine you have multiple worker. How do we model this kind of case? Still complexity analysis. So you see that we have 2 phases. I think the second phase, we know how to quantify that. Given the fixed numbers of cities, which is 5 each, you try to come up with the best possible result, right? So I think second part is easy. We do it the first. So for the first salesman, you have 5 cities, which means that your n equals 5, right? So you have 5 minus 1, and this particular map over here, is symmetric, right? This is the key phrase. The distance is the same in opposite directions, right? So which means that you can also divide that by 2. So this particular doubting consideration will be repeated, right? For the first salesman, you're going to go through this. For the second salesman, you're also going to go through this, right? So you have 2 components. But before that, you have to decide which of the 5 cities get to assign to which, right? So you have the first salesman. Out of the 10 cities, you pick 5 cities for this salesman. And then, like, the next thing that you do is that you only have 5 remaining cities, right? So no choice, it has to go to the second salesman. Okay, so that is the part. I mean, this part for completeness, we still write it, but this is simply one, right? Only one possibility. So the real complexity actually comes from here. Out of 10 initial CT, you have to decide which of the 5 CT belong to the first salesman. All right, so these are all the unique type of assignment and also the routing choices, right? So after you make the decision, which particular CT goes to whom, then you route them individually, which is provided by the TSP formula. Right? You go back, that is the final formula, which is being listed over here. The first one is actually very close. The only part that's different is that this part, you don't really need the square because this only occur one time, right? Only the first salesman got to choose out of 10. For the second salesman, you cannot have duplication. You have to you have to serve the remaining 5 CTs. All right, any question? Right, let's take a 20-minute break. So use the break to find your teammates, get to know each other, leave your contact. Make sure that you make good progress next week. We will take a break until 1:50. All right, so I think the first few questions mostly done. I think 6 to 9. I will just very briefly go over that. So for number 6, this is still complexity analysis. So if you go back to Q1, over here, this is what we have from the slide directly. You have a certain numbers of CTs. You can say this can be n. I mean, over here, n equals 20. Two different scenarios where the cost, number one, the cost is symmetric. This is the case that we have from the slide. And the second case is the case where you actually recognize that clockwise and counterclockwise way of performing the tool will give you different costs. So if you look at A and B, the major difference is that the first part will be n-1 factorial divided by 2, while for the second one, you do not do this divided by 2 since clockwise and counterclockwise will be considered different, right? But the complexity still have this n-1 factorial because you have a tool. So as mentioned, having a tool is almost the same as you try to line up you try to seat your guests around a circular table so you can rotate your starting location, but no matter where you begin the trip, because you still need to go back to your beginning location, so it doesn't make any difference. All right, so for number 6 over here, you say that we take away the requirement that you need to return back to the starting point. This will make your complexity calculation side differently. I think all of you, or most of you actually get it correctly, but just probably using a very simple illustration to demonstrate why that is the case. So let's say you have 3 CTs, A, B, C. In the previous case where you have a tool, the actual path is actually, if you just broke it down, is going to be AB plus BC plus CA, right? You have 3 CTs, so 3 ages. Or if you want to visualize that, it's something like this, A, B, and then C, but you still have to return back to A, right? So now for question 6, what you are looking at is you just want to traverse from the origin city to destination city, but you do not need to go to the origin city again. So what you have is AB plus BC. That's it, right? 2 ages. Okay, so now we can try to rotate. For example, in the previous case, we can, instead of beginning from A, we can begin from B. So in this case, you have B, C, A, but then you return back to B, right? So if you write down exactly what is the corresponding ages that you accumulate along the way, if we just do a one-to-one matching, what you have is BC plus over here, right? You have CA, but then, right, you do this AB, right? So what's originally at the beginning now appear at the end, but it's still the same. So if you rotate again, you can imagine, right? So if we want to do another rotation, this is what we'll be getting, right? You start from C, you have C, A, B, but you return back to C, right? So if you just do this again, you have CA plus AB, and then plus CA, AB, BC, right? Three different ages, but their cost will be exactly the same. And if you look at the exact relationship, precedence relationship, they will actually be exactly the same. B is always after A, C is always after B, A is always after C. No matter how many CT you have, it's always the case. That's why you have, if you have n factorial, you divide that by n, right? All the different potential starting place will give you exactly the same tool. And then additionally, you also divide by 2, because if you do it this way, you do it this way, you will produce exactly the same tool. Okay, so now you look at the second case here, you do not have that property anymore because you do not return back. So you have ABC, you can have actually BCA, right? In the previous case, this is considered the same because you return back to the original place. But in this case, right, you see that this is BC plus CA. They are not the same anymore, right? For the first case over here, you are missing AB, right? And for the first case, you are missing CA. While in the previous case, both are actually inside the formula. This AB actually is actually inside, right? So this is what we are missing. So if you rotate again, let's say you have CAB, for example, in the previous case is considered the same, but here you miss, you have CA, you have AB, right? So again, it's different from the previous two because you I mean, for each and every permutation, you miss one of the element, right? If you compare any pair, they are always like one missing in each. Okay, so this is, again, if you want to make an analogy to the earlier counting problem, this is like you try to line up n numbers of peoples in a straight line. How many different ways where you can line up then, right? But in this case, this is like you try to assign people to seats around a circular table. How many different ways you can make the assignment, right? So in this case, for part A, where the cost is symmetric, you can still do clockwise, counterclockwise, but you cannot divide by n. So you have n factorial, but only dividing that by 2. For the second case, if it is not symmetric, then you cannot even divide by 2. You only have n factorial. Okay, so that's the first part. Again, check your solution. I say mostly correct. Yeah, I think all of you did it correct, right? Except probably 1 or 2 missed cases, right? Okay, and this is the detailed reason behind why we have that solution. This is number 6. So now we look at number 7. This is the analysis of complexity. Again, mostly correct, right? But I think we have some discrepancy in answers. So let's go back to the actual algorithm, right? We want to perform the analysis, so we always just look at the actual algorithm over here. We look at greedy one first. We just clip it. We will perform analysis directly on the algorithm, right? So this is the sequence that we plan to analyze. All right, so this one, okay. So we do it step by step. Yeah, so you are given initial CT. So this part doesn't really cause any time at all. So this is constant time, right? Only one CT. So the real complication really come in here, right? So you want to find the CT X inside the remaining set as over here. So again, over here, just a demonstration, right? To illustrate, if you want to analyze this systematically, again, it's recommended that you try to use table to tabulate like all the effort over different choices. In this case, your outer loop are like numbers of CT you have gone through, right? So you start from, for example, CT1, CT2, CT3, right? In total, you will only go through n-1 CT because the first CT is chosen for you. Okay, so when you are entering the while loop, you're looking at the very first CT, right? With that will be your initial CT. So you will be looking at the numbers of possibility, right? So this is where the real effort come in. So numbers of possibility, right? So possibility basically are the remaining CT. When you are having one CT inside the selected path, you will have n-1 CT that you should be looking at. So what you do over here is that you're going to go through, right? So suppose your agency list is not sorted, doesn't follow any specific structure, then you have to follow, you have to go through n-1 possibility to pick the one with the smallest cost. Right, so let's say you pick that one. So now you have two CTs in your path, but in terms of option, when you are about to choose the next candidate, you only have n-2, right? So you continue the process. You can repeat a few, and then you'll see the pattern, right? When you already have n-1, then you only have a last CT to choose from, right? Really, there's no comparison needed, right? But that's the indicating how many CTs, how many CT candidates you will need to look at for each and every step. So in this case, although it's a while loop, but you know exactly how this particular while loop begins. You begin with one CT, and then you will end the last loop inside this while will be the case where you have already n-1 CT in the past, and you are picking the last CT, right? And then you sum up all the efforts through the iterations. This is sum of your arithmetic series. So 1 plus 2 plus until n-1, right? So we have done this many, many times. It's going to be n multiplied by n-1 divided by 2, right? So that will give you n squared complexity. Okay, so this is how we actually analyze the pseudocode, right? And then we use, again, we will try to, whenever possible, stick to like a systematical way of doing this, right? Don't guess, don't try to just like come up with arbitrary way of evaluating complexity. Just try to tabulate the effort you go through all the iterations, right? Usually you can, I mean, if this is the well described pseudocode, usually this is possible, right? So this is for greedy one, relatively easy to analyze. So now we look at greedy two. So again, we look at the pseudocode that's given to you. I'll use this one for the purpose of analysis. Let's take this whole thing. And then we analyze all the steps, following very similar steps that we have just gone through. Okay, make it smaller. Right, so this is what we have. We have a preparation step, which is picking the initial tool. Remember, the way that we pick the initial tool essentially is that we look at the whole matrix, right? This distance matrix. We pick the pair that with the lowest value. So effectively, what you are doing is that you look at this. In total, you have n squared elements. You have to look at, I mean, in the worst case, each and every one of those elements and pick the ones that's with the lowest cost. Even in the case that you assume that, for example, the matrix is symmetric, you still need to look at half of those elements, right? The upper triangle or lower triangle, because they are symmetric, right? But the order of that will still be n squared, right? So this particular step picking the initial tool will be n squared divided by 2. All right, so this is the first one, which means that the whole process is at least whole n squared, cannot be less than this, right? So, but then after that, we have this while loop. Again, you will try to analyze this step by using a table. It's actually possible to use the table to analyze that. Here, this I over here, because what you are really growing in this particular while loop is actually the set of t. Your t start with 2 CT in it, but every iteration, you will insert one candidate into your tool set. So as a start, you have 2 CTs. And then after you finish every iteration, the size of t will be increased by 1. So you have 3, you have 4, 5, right? So on and so forth. Now, again, you want to find out when is your last iteration. You will face the last iteration when your t contains n-1 CTs, right? So this is the time that you're going to pick the last CT and decide where should you be inserting that CT into. Okay, so now we actually have a row. We know that exactly how many times this while loop will execute. Now we look at, again, the amount of numbers of operations, or simply the efforts, right? So let's see how we quantify the efforts. So for the case where your CT contains only 2, effectively what you do is that for each and every candidate, you have to evaluate them, right? So because it's only 2 CT in the tool, it means that you still have n-2 CTs, right? That's actually inside the set S, that's the candidate list. And for each and every element inside that candidate list, we want to evaluate what is the smallest distance that it takes you to connect to tool T, right? But currently tool T contains 2 elements, which means that for each and every candidate in S, you will spend like 2 comparisons to look for the smallest distance to connect to T. So when you have n-1 candidates, every one of the candidates you need to spend 2 lookup, right? 2 comparison, right? Okay, so this is the first thing, right? Of course, you have some other things, right? Because after you have make the decision, you have picked which one is the smallest. You have to compare the 2 cases. You insert the final chosen candidate in front of the connection point or after the connection point. That's 2 operations, right? Okay, so now let's say you have made the choice. You have expanded your T to contain 3 elements. Your candidate now is decreased by 1. You have n-3. But if you look at the amount of effort per candidate, for each and every candidate, now you have to evaluate 3 different ways where you can connect to T. And you're going to find the one that's with the smallest cost, right? So for each and every candidate, now you have 3 operations. Then this part is constant. The second part is constant, right? Okay, now you have 4, right? I mean, we can just do a couple times to make sure that this pattern persists. Now, in terms of numbers of candidates, you have n-4. But for each and every candidate, again, because tool contains 4 different cities, you have to evaluate your connection to each and every one of those 4 cities. So the effort will be 4 per candidate. This just keep going, right? So if you just keep going, what you have when you reach the last one, you only have a single candidate. But for this particular single candidate, you actually have to look at all the remaining n-1 connection that you potentially can make inside the tool T, right? To find the connection point. So this is your pattern, right? So if you look at the pattern, you can see that it's a multiplication of these 2 numbers. You have to sum up everything, sum up all that, right? And then the pattern is a n-I multiplied by I. That is the pattern. And this is the sources. This is how we can calculate the complexity from, right? So if you want to write down all this, I mean, of course, you can just write the whole thing. But you can actually use the summation sum to represent that your I will go from 2 to n-1. right? And then your general formula is actually n minus I, which is the first part, multiplied by I, which is the second part, and then plus 2. Okay, so this is the exact complexity. So now we can expand this, right? If you expand this, inside here, you have n times I minus I squared. Sorry, should be I squared. And then it's going to be plus 2, right? And this is from I from 2 to n minus 1. Right, so the second part over here, right? So I mean, if you just pull it out, what you have is that you have this n. I mean, the first part will be summation from 2 to n minus 1, I, right? And then minus 2 to n minus 1, I squared. And final part will be 2 times, if you look at it, the numbers of terms that you have, will be what? N minus 1, n minus 2, right? Okay, so that is we'll directly just find like how many terms that we have. Okay, so now really what you have is 2 parts. You have the summation. This is arithmetic series sum. This one we know. This is summation of squares. If you still recall, right, we actually have a formula. You just like flip back. I think maybe week 3. I think one of the complexity question, we actually give you this formula, right, for the summation of I squared, and then go from 1 to n. What's the formula? Okay, forget the exact formula, but it's roughly in the form of this n times something multiplied by this times something divided by 6. Right? But the important thing is that the highest order term in this case is actually n cubed. That's the thing you want to know, right? And this is the subtraction. But for the first part, right, this is the sum of arithmetic series. So this, we know that, I mean, this is the first term 2. The last term is n minus 1. Numbers of terms against n minus 2. Multiplied by the summation of the first term, last term, n plus 1, right? Divided by 2, right? So the highest order term, again, is n squared, but you have to multiply the n that's in front. So the first term, again, if you wanted to write it down, it will be by n cubed. The second term is also in the order of n cubed. The last term is actually on, right? And then again, you remember at the beginning, the preparation phase, you have a n squared. So this whole bunch of things sum up together, you pick the one that has the highest order, that will be n cubed. That's how you derive at the n cubed complexity. If you want to do it, exactly, no. But if you want to just very roughly estimate this, okay, this is another way to think about that, right? So somewhere, again, not recommended, but let's say during exam time, really, you don't know how to do it. Just imagine that, I mean, once you write it down as a table, you look at somewhere in the middle, right? So suppose you reach the point where is n divided by 2, right? Then the formula over here, the pattern here will tell you that the other side is also n divided by 2. So again, roughly speaking, again, not very scientific, but roughly speaking, this seems to be n squared for each and every line, right? So then because you have here, this is in order of n minus 2, this is how many rows that you have. So roughly speaking is n squared times n minus 2, that will give you also n cubed. Not recommended, but if really you have no idea how to proceed beyond this point, this is one way to help you, right? But if you can write it down in a general formula, this is the recommended way. How do you accurately quantify the complexity using this formula over here? Okay, any question for this one? Yep. Yeah, so this one we look at here, right? I mean, you just imagine really what we are doing. We are searching for the lowest value. And in total, I mean, you have NCT, NCD, so the size of this matrix is n by n. But suppose the matrix is symmetric. It means that you only look at the upper triangle, right? So that's half of the element. The lower triangle, you can skip it, but it's still in the order of n squared, but it will be n squared divided by 2. All right, other questions? Yep. Oh, yeah, because for after we have identified the connection point, we have to evaluate, do I insert this candidate city X in front of Y or after Y? 2 cases, right? So that will correspond to over here, these 2 steps. But this is only accumulated after you have picked the one as the candidate. Then you accumulate this additional 2 calculations. But it turns out to be non-consequential because it's a summation. And when you multiply by n minus 2 rows, this is only in the order of ON. So it would definitely be overwritten by both n squared over here and n cubed for the first 2 terms over here. Right, other questions for this part? Okay, so this is complexity. How do we do it exactly? This is for question 7. Question 8, I think again mostly correct. So I think no big deal. The tracing of the algorithms are all correct. And it turns out that, this algorithm actually is not very good. Also, if you have highlighted a lot of examples, all of them are more or less valid. But you just use a particular example. For example, if you want to go from B to D, right? Let's say you follow this greedy strategy has been highlighted over here. You always pick the one that with the lowest cost. What you will do is that, for example, out of B, although you intend to go to D, but the first node that you choose will be E, right, which is in the right direction. But from E, you see that if you follow the lowest cost option, you go to F, and from F, you go to A. And by this point, you are stuck, right? Because you cannot visit the node for more than 1 time. You usually you cannot even reach your final destination, right? So this is different from TSP. TSP, it doesn't matter how you choose the sequence because all nodes are connected, so you can always finish a tool. It's just that it's going to be a long tool, but it's still going to work. But here it doesn't quite work because not all the nodes are connected to each and every other nodes, right? This graph is not a complete graph, so very likely you're going to get stuck somewhere. Right, so that is the reason why we have the UCS to guarantee that you can always find the path. This is number 1, and then you find the path that's with the best cost. Right, so I think the purely greedy principle in this case is almost like you just try to find the path. Remember, when we talk about UCS, we say that if you instead of only using the G function, you add a heuristic function, H function, you can improve the performance. This is like you only use the heuristic function, but you're not using the G function. In this case, you may not be able to find a possible and feasible route to reach your final destination. Okay, so this is number 8. I think, all of you get it correct. So number 9, I think this is an interesting question. If you contrast that against the earlier question, if you look at the earlier question, number 4, this is actually if you look at solution, this is the perfect case where even you just use a greedy approach, you can actually find the optimal, right? And the reason why this is the case, again, if you contrast 4 and 9, is because you look at number 4 is always optimal because even in the case that you follow the optimal strategy, because all the coin denomination, they are multiple to each other, right? If you look at, for example, like 10 cents is like multiple of 10 cents equals like 1 level up, which is 20 cents, which means that whenever you can use 20 cents, you're going to use it because there's no point just use 2 lower denomination coins for the purpose of a single 20 cents, right? So you can always achieve the best possible result if you follow the greedy principle. Like the use of 1 coin with a more higher value will always lead to like more coins with lower value. Okay, so this is the case for number 4. But for the case of number 9, this is not a case. And the reason, the major reason why greedy will run into difficulty, it still can give you a valid result. It's just that the result may not be the optimal. And the major difficulty is over here, right? So you see that from 5 to 35, 5 is a 35 is a multiple of 5, which means that if you use 135, no point to just divide up the value and you use like 5 cents, right? But 60 cents is not a multiple of 35, which means that if you have a multiple of 35, the greedy approach will not recognize that because the closest value will be 60, but 60 is not multiple of 35. So what you will end up with is that you miss the opportunity to use the multiple unit of 35. Instead, you use 60, which is not a multiple of 35, together with the other smaller denomination coins. Give you one example, right? I think all of you give like example which are all valid. But the simplest example is just to have a multiple of 35, right? So if you have, let's say, 2 35 coins, you will have 70 cents. But if you do the reverse engineer, right? So now you say that if I request 70 cents, I follow the greedy principle. I will use the closest denomination, which is 60, right? And then, but after I use 60, I lose the chance to utilize 35. So in return, I can only use 2 5 cents, right? So that will be a very easy way to construct an example that's not optimal. And also, if you look at, this is the relationship between 35 cents and 60 cents. Another example is you look at the other case, like $1 and 60 cents. They are not multiple to each other as well, right? Which means that if you have 2 60 cents, you apply, again, it's only 2 60-cent coin, but if you apply the greedy principle, $1 will be utilized first, but then once you utilize $1, you lose the chance to utilize 60 cents. You can only make it up by having like 4 different 5 cents, far from optimal, right? So I think for this case, it's very easy to cook up example where the greedy strategy will fail. And this is the reason why if you go to most countries, for example, like you look at the coin system in Singapore, or you look at the coin system in the US. In Singapore, we have $1. You have what? 50, right? They are multiples. They are multiples for a reason, right? And then I think after 50, we have what? 10 cents, right? And 10 cents after that, you have 5 cents. So, this is, I also have 20 cents. Okay, 20 cents, and yeah, it's probably not so good an idea, right? So because you see that if you just follow greedy principle, potentially, you can have a loss, right? But for all the other cases, I think if you look at these cases over here, not so good. But if you have multiples, then I think over here, that will make the designing of, for example, automated mechanism very easy. Automated mechanism, for example, vending machines. Your vending machine now is much, much simpler. You just follow greedy principle, very easy to code up, and then you can always find the optimal numbers of coins for the transaction, right? So this is number 9. Number 10, I think it's mostly done, right? Okay. Yeah, probably halfway there. But again, over here, in the interest of time, just briefly mention that this is another practice of how to design the greedy approach. The key to design the greedy approach, again, you have to first identify what is your objective. The greedy approach basically divide up a combinatorial consideration into one choice at a time. And you're going to make the choice, this single choice, repeatedly, right? So over here, you can see that the objective is to minimize the sum, right? This is a keyword, minimize the sum of absolute difference between the height of the skier and the length of the ski, right? So again, to get the optimal answer, of course, you have to look at all the skier simultaneously, right? But to make the process simpler, you want to, let's say, to handle one skier at a time. but still somehow like try to approach this particular best possible solution that you can achieve, then what you do is that instead of looking at all the skier, you look at single skier at a time, but you still use this absolute difference between the height and also the length as the selection criterion, right? So you look at, for example, the differences between among all the possible combinations, and you pick the one with the smallest value, start with that. And then that basically means that you take away the skier, you take away the ski, and then for all the remaining combinations, then you begin to pick the next best, right? So you have a 5 and 5, which means that, again, we didn't really ask you to do that. The question didn't ask you, well, actually, we actually do analyze the complexity, right? So if you want to analyze the complexity also, just imagine that you have 5 by 5 initially, right? But in the general case, you have n by n, right? Okay, so this is initially the numbers of choices you have to look at. In total, you have n squared cases. So now after you make one choice, right, the numbers of choices become n minus 1 squared, right? Because initially you have 5 by 5, but after you make one choice, it's only 4 by 4. Right, so you'll continue the process. The last one, really, no choice need to be made. In the second to the last, you have 2 skier, 2 skis. You have 2 by 2 combinations. You pick the one that with the lowest value, right? Okay, so that will be, roughly speaking, the complexity we are facing. So in total, it will be sum of the squares. We have just looked through that, right? So that will give you, again, the exact formula, you can look it up, but roughly speaking, that will give you the n cube complexity. Okay? Very quickly speaking, right? And of course, this is this is based on the assumption that you actually do the searching for the smallest value every time. But of course, this is a kind of a redundant step, right? Because if you have n squared values, one potential thing you can do is that you only need to like come up with the rank for one time, right? I mean, you can probably use the sorting algorithm. You can sort them. You have an n squared value, right? So in total, if you sort this n squared value, roughly speaking, you have n squared times log n squared. That gives you n squared log n. It's still n squared, and then multiply by log n, but at least it's going to be better than n cubed. Right? You do it one time, and then for the remaining of the iteration, you just need to update. I mean, for the value that doesn't belong, it has been chosen, is not valid, you can do delete it, right? For example, right? But roughly speaking, if it is sorted, then is I mean, you do it at the very beginning, you will benefit the later iterations. But the design need to be very careful, right? But if you do it in a straightforward manner, it's going to be n cubed. All right, so I think time is up. So we will probably stop here. But if any question, welcome to stop by to ask. Otherwise, again, remember, there's no class next week. So please use the time well, focus on your project. It definitely requires a lot of tinkering, so just set aside time for that purpose. And then ask question on the forum if any part of the project is not clear. All right, so I will see you in 2 weeks.